Welcome, everybody. We're hoping everyone can find the room, so we may have people wandering in. And thank you for coming to this room. Fourth term has always been on the second floor, and I think that the next lecture will be on the second floor, but make sure you always look to see where it is, because I'm going to go down and talk to them today and say, how come we got a different room? It's confusing. Anyway, but thanks for coming here and finding us. We're really lucky to have today's speaker, Michael Weiss. And I just want to say a few things about why I think we're lucky. So he's giving a talk about education. He's involved in education research. And when I first talked to him, well, first I called a colleague at Vanderbilt and I said, who's the best person to talk about education randomized trials? Right away, he said Michael. So then I said, well, what about doing something on cluster randomized trials? He said, well, we don't do those in higher education. They're done in like K through 12. And I'm doing research on higher education. And I said, well, you got to throw a cluster in, so we did. But that's interesting to me that cluster randomization is not used in certain types of educational studies, and is used in others. So maybe questions or whatever will come up. It's a very informal group that asks questions along the way. So Michael works at MRDC, which in the old days used to be called Manpower something. And
Demonstration Research Corporation.
Okay. Now it's MRDC. Obviously, manpower is not a word anymore. Person power, or per child power, as some people would say. And they do a lot of the educational randomized trials. And the questions that I had dinner with Michael last night, and the questions that they're asking are, and the methodologic questions they're dealing with, they're very close to what we're dealing with. We're just in different fields. So. And MRDC deals with social issues, not just education, but other things like welfare and criminology, and social issues anyway. So we have a lot of the same issues, and yet we travel in different worlds. So the idea was to bring these worlds together a bit. I'll tell you first a little bit about Michael, and then he can do his seminar for you. So he's led numerous randomized trials. He did his undergraduate degree at Cornell and in applied statistics, and then went on and did a PhD at Penn in education policy. And then I think directly went to work at MRDC, is that right? Okay. And so he's been involved both in doing randomized trials as to what works at the community college level, and also methodologic research. And the methodologic research is like teacher effects. And I thought of Swart Root. I should have let him know because he's interested in surgical effects. You know, the effect of the surgeon in a randomized trial. And it's a teacher effect in randomized trial. And so very similar questions here that, we should be talking, basically. He's also talked about measuring school performance and the uncertainty of effect estimators in individually randomized trials, and then the conceptual framework for understanding the sources of variation in program effects, which of course we talk about all the time. And last night we talked a lot about evidence synthesis, which I think there are some people in education who are doing this, but others who are just sticking with the randomized trial. So it does seem like this is an area of potential overlap as well. But I'll let you get on and talk about and do your topic. This group tends to be very lively and ask a lot of questions. And then people have to go to class around 9:30, 9:20, 9:20.
Great. Thanks. So thanks for having me. I agree with Kay's points. It's interesting that I tend to hang out with all these people that are doing education research and a lot of education randomized trials. So it's nice to get to spend some time with people who do similar related work, but just in a different field, because I'm sure there's things we can each learn from each other. If you're super interested in cluster randomized trials, which I'm not really going to talk about, feel free to ask questions, because although I haven't really been involved with them, because as Kay said, in higher ed, they're really uncommon. But the company I work for, it's actually MDRC, not MRDC, but But we do work both in K-12 and higher ed, and in our K-12 group, where I'm friends with lots of people, they do a lot of cluster random assignment studies. So I can speak to it, even though I haven't actually done them myself. So MDRC is a nonprofit, nonpartisan social policy research firm. We actually originally started doing work in the welfare reform area about 40 years ago, and kind of pioneered, I think, doing randomized control trials in that area, as well as in higher education, where in 2001, I think we conducted probably the first large-scale randomized control trial in higher education that I'm aware of, at least. So I'm going to talk to you about an issue that arises and is of interest to me when you do individual random assignment studies, and then after people are randomized, they end up being grouped together for oftentimes treatment delivery or service delivery. I want to thank Kay for inviting me here, because I think it'll be really fun for me, at least, to do this, and hopefully you'll find the topic interesting, and if you don't, just blame her, because she was the one that thought this would be a good topic. So I'm going to be focusing on randomized control trials. Just so I can get a sense of the room, who's actually worked on a randomized trial in the room? So almost everyone. Good, nice. And who here has done more work on like non-experimental, more like matching kind of studies? No one. Wow. All right. That's interesting, because in the ed world, at least in the past, that was like the exact reverse. Like everyone had done propensity score studies and kind of no one had done RCTs. And then over time, that seems to have shifted in the last 15 years. But it's interesting to see that here, no one, I guess, is doing that kind of work. Okay. So there's two parts to what I want to talk about based on two papers that I've been involved in writing. One is about conflating treatment effects with service provider effects, which in the paper was called teacher effects, but for you guys, it's probably like doctor effects or therapist effects or whoever the service deliverers are in your sort of world. So that's part one. And then part two is about estimating the standard error of the impact estimator when you have an individual random assignment study with post-random assignment clustering, and how that can be kind of tricky. And that is joint work with two other researchers who, if you're in education, their names mean something, but if you're not, they probably don't. So, but I should give them credit because they helped me out a lot with that second paper. I don't know if we're going to get through them both. We'll see how many questions you guys have. I think we'll definitely get through part one. We might get through part of part two, but hopefully you'll get the idea from getting through whatever we can get through. So. All right, so part one, and this is like super easy and obvious, and maybe like in your world people have talked about this and thought about it a lot before, and in education it was just kind of new. But it's about this idea that when you do random assignment of individuals and you don't randomly assign people at the higher level, like the doctors or the teachers in my world, that you don't really know if the effects you're estimating are about the treatment that you care about, or if it's just the service providers were better or worse in one group. And I feel like I could probably stop right there, but I'll go through the details of it. So what motivated me to be interested in this topic was that the first study I was actually on when I was working at MDRC was an evaluation of learning communities. It doesn't matter that much what the intervention was, but just in case the context makes it more interesting, it's this idea of co-enrolling students in 2 or more classes when they begin community college. And the faculty that teach those classes are supposed to collaborate and have joint assignments and assessments. And I'm kind of going to oversimplify the intervention, but the main point is it's an intervention that people thought was an effective way to help students be more likely to earn credits and persist in school and be more likely to graduate eventually if they were to sort of do this learning community. So we were doing this study to figure out what the average effect of learning community was on student academic progress and eventually completion. So that's kind of the background. Our study design was we randomized individual students. And then after students were randomly assigned either to the program, what I'm going to call arm, or the control arm, or treatment arm, or control arm, I'm going to use arm for reasons that will become obvious later, hopefully. Treatment group students, they self-selected into the learning community that they wanted to be a part of. So that's an important thing. They kind of chose there were lots of sections that were available, and they could choose. If you were in the control group, you couldn't sign up for those learning communities. You just kind of sign up for regular classes. The important thing, so the treatment was delivered at this group level, but the really important thing is that the instructors who taught in these learning communities, they were recruited. And we did implementation research and kind of learned that some of them were like really enthusiastic. They loved this idea of learning communities. Some were kind of like maybe forcefully coerced to participate because their department chair kind of said, hey, we need some people to do this. And then later in the study, from what we heard, people kind of liked this, so then more people were like volunteering to teach in these learning communities. This was like a multi-semester study. As other tiny pieces of information that you might care about, there's about 1,500 people in the study, half in the program group, half in the control, or half in the program arm, half in the control arm. So the reason I'm using arm for that is because then I want to refer to people who end up in the learning communities as part of a group. So treatment and control arm, and then you end up in groups or clusters afterwards. So the important thing is that instructors they self-selected into whether or not they're going to teach in learning communities, or on the control side, you just had whoever ended up not self-selecting and they were just teaching in the regular classes. So here's my pictorial, my visualization of this idea. So we're going to have our treatment arm, our control arm. And let's just say we have kind of good and challenging students. There should be a G there under challenging. And we have effective and ineffective teachers. So at level 1, we have our students. For you guys, this is probably like patients. And this is my visual depiction of randomization. They all kind of get randomized. And lo and behold, it's wonderful. You end up having two groups that are approximately similar at the beginning of the study. Some that are going to be in learning communities, some in the control. And the tricky thing here, though, is at level 2, we've got these teachers. And it could turn out that kind of the more effective teachers self-selected into the treatment, and the less effective teachers end up in the control. And then as a result, when we look at the differences in the outcomes, we're not going to know, was it really the learning communities that made the difference, or was it just about the teachers? So does this make sense? Is this the kind of thing that might happen in your world, like with... Yeah, all right, nice. So check this out. My next slide, I tried to make what I thought you guys might think was like related. So you have your level 1 patients and your level 2 surgeons. Maybe you randomly assign people to end up getting some new form of surgery, but only certain surgeons have learned how to do this procedure. I don't know, this is like me making things up. In fact, I even went to one of the websites where one of the faculty here was, and was like, let's say there was a treatment that was 2 surgical procedures to treat primary open-angle glaucoma. That sounds fancy. I don't know what that means, but it seems to be a thing. And this could be what happens. And then you're not really sure whether or not it's the surgeons or the actual surgery that's making the difference. So that's the idea. So first of all, it's just a problem. I feel like that alone seems important to recognize. One thing that we did to sort of think about, is this just like a theoretical problem, or is it a potentially real problem that we should be like very concerned about? Was we made an assumption, which in the education literature, like people have studied this, about how much teachers' effectiveness varies. And there's some evidence from actually studies where they randomly assigned students to teachers, which allowed you to then estimate the variability of the teacher effectiveness distribution, if that makes sense. That basically teachers seem to account for around 10% of the variation in student achievement at the end of the year. Most of what it is just kind of where you came in the first place, but then around 10% of the outcome variation is a result of teachers. So what we did was we then said, okay, let's say you calculate the impacts for the core components of the program, like in this case, learning communities or your surgery, under different possible teacher selection scenarios. All right, so does this make sense? It's sort of like a thought exercise. So here's actual results from this trial that we had. In the program group, the average number of credits that students had earned, I think this was after like 1 semester, was 11.5 credits, 10.4 for the control, and the estimated effect was 1.2 credits. And this was like highly statistically significant and seemed like a pretty exciting finding. Standard deviation of the outcome, which will be relevant for the next calculation, was 7.2. So we then said, are people familiar with interclass correlations? Is that like a familiar term? Yeah, okay. For those of you that's not, it's basically a measure of how much variability there is between, in this case, classes. And it's one way to think about that idea that 10% of the variability in outcomes is attributable to teachers. So you kind of, this is sort of like a formula for it, where tau is how much variation there is between classes in my world and maybe doctors in your world. This is the total variance of the outcome. And so if you're assuming that 10% of the total variance, that's going to be the ICC, is 0.10, and your control group standard deviation, that's going to be the whole sum of the outcome variance, is 7.2. It suggests that tau, which is how much variation there is between classrooms, is around 2.3. You don't have to really understand all this to this makes sense. The important thing is it kind of suggests the following graphical representation. If you have the average teacher, you're going to have somewhere between these two numbers, like you're going to earn around 10.9 credits. And this is sort of like the teacher effect distribution. So if you end up getting like the really good teachers, you kind of expect you might earn around 17 or 18 credits. If you get the really bad teachers, we expect you're going to earn around 7 or 8 credits. Does that kind of make sense? Yes. Okay, good. All right, so the next thing we did was then, another way to think about this then is to say, okay, if you had a 30th percentile teacher, you're expected to earn 9.8 credits. If you have a 70th percentile teacher, you're expected to earn 12.1 credits. And so if we compare these things, the difference in mean credits earned for students with 30th to 70th was 2.4 credits. The treatment effect was only 1.2 credits. So This is to say, like, if it turned out that in this study, the learning community teachers were like 70th percentile teachers, and control group teachers were 30th percentile teachers, it could be that actually learning communities were harmful, and all you really did was kind of recruited your best teachers into learning communities, your worst ones into the control group, to teach the control group, and then you thought there was a positive effect from something that actually was harmful. So this is a little scary, maybe. I don't know how to think, and no one has given me any good ideas, but maybe you all have some, about is it realistic that the program group would have ended up with the 70th percentile teachers and the control with 30th percentile teachers. We just don't have like great measures of teacher effectiveness, especially in higher ed.
You don't randomize the teachers, do you?
That's the whole problem.
Yeah.
It's because you don't that this could happen. Yeah, if you did. Yeah. Well, and that's one solution, right? And that would be kind of more like a cluster randomized trial. Why don't you do that? There's faculty unions. Instructors don't want to teach learning. Some instructors don't want to teach it, and so they're just going to like not do it. Yeah. Yeah, it's totally for practical reasons. It's not because we wouldn't prefer that. I mean, there's some power issues that occur there as well, but yeah, it's basically practical reasons that we don't do that.
Well, no, I could get it for certain tracks. I just didn't get it here. And then I also thought it wouldn't have to be clustered. You could randomize the teachers, and then you could also randomize the students to the teachers.
That's true. Yep, that's true. Depending on how you end up analyzing the data, you still will lose power to some extent there. Yeah, you still might lose some power there. Do you disagree, or should we talk about it? Okay.
I think it would be very complicated.
Yeah.
I just thought it was possible.
Yeah. And there's one instance I know of where that kind of thing was done, and it was like a very small mentoring program. And what they did was this was true cluster random assignment in higher ed, where they basically took a whole bunch of these student success courses. In community colleges, students come in usually like very underprepared, and oftentimes they don't have like appropriate pretty basic study skills. So they have these classes that are about study skills and goal setting and kind of just like navigating life in college. And so somebody actually did a randomized trial. I think actually we did a randomized trial where we randomized sections of these student success courses to have some sort of mentor come in and give some help to the students in it. So that is an example of where you would kind of overcome this problem. But more questions? Okay. So I just gave kind of one example because I wanted to show it on the distribution, but what we also then did was we tried to think about this across an entire distribution. So on this graphic, let me explain it before anything comes up. On the y-axis, I have what I'm considering like the true effect of learning communities. Well, that's probably like the true estimated effect, but then the true effect of learning communities. And on the x-axis, I'm going to have what I'm calling bias, which is just the percentile difference between your treatment and control group instructors that just happened through this self-selection process. And so let's just say that like it turned out by chance that the learning communities teachers were 50 percentile, they're kind of like average-ish instructors, and the control group were 50. That's what my 50p and 50c is supposed to mean. If that were the case, then our best estimate of the true effect really is 1.2 credits, right? Because there's kind of no bias introduced by the differences in the teachers. But then this other dot here, this is 70-30. That's the kind of extreme example that I gave before, where it turns out that the program group kind of got all the best, or 70th percentile teachers on average, and the control group got 30th percentile. And you can see if you had that, then your impact estimate would actually be like somewhere in the negative 1.2. Like the true effect of learning communities would be, they'd be harmful. And then you can just kind of fill in the whole gamut of possibilities, and sort of see, depending on how much teacher self-selection there was, and what percentiles they were, how would that have changed what you thought about? This is just like a way of trying to get a sense of like how worried should you be about this. And one thing that I thought was interesting to do is then say, well, at what point would we have changed our statistical inference? Like at what point would we have not concluded that these learning communities were effective? And so this is sort of the line below which, at least in higher ed where people seem to still value very much statistical significance, this is the threshold where it would have our results would no longer have been statistically significant. And it involves the program group teachers being around, I think, the 56th or I can't remember if it's 56th or 54th percentile, and the control being around the 44th or 46th. I might be getting those numbers mixed up, which to me feels quite possible. Like, I feel like the 70-30 feels pretty extreme. Like, I don't know how much selection there is of who went into the learning communities and if they're like the best and the worst, but it does seem totally possible that like the program teachers, the ones who self-selected to teach learning communities, were like a little better. Yeah, so this is, so at least to me it means like there's reason to be concerned that like it could be that the effects we're seeing are more about teachers than they are about the program itself. Does that make sense? Yeah. Okay, so, yeah.
Assuming that standard means or standard teachers, but I think the students can like a teacher for other reasons. So let's say all young people, all young teachers, maybe the students like them longer than closer to their own age. And they're just as good teachers, whatever that means.
Yeah.
But it really is 70-30.
So I used effective versus ineffective intentionally because I'm like defining effective versus ineffective as those that will increase the kind of credits you'll earn versus decrease it. And it could be that that's related to some more observable characteristics like age. It could be that you have very different age teachers in the program and control group, but if they're equally effective, I would count that as 50-50. Yeah, it's not the, I don't think it really much is in the same way like in a non-experiment. Like, it doesn't really matter if you don't have balance on unobservables that don't relate to the outcome. In this case, it doesn't matter if you have teachers that kind of look different as long as they're not any more or less effective than each other. Yeah. So I would actually go even further because you could have an infinite sample and perfectly precisely estimate the treatment effect, but the problem is that it's biased. It's not a precision issue. So if you, let's say this study had 1 million people in it and actually our estimate of 1.2 credits was like, the standard errors was near 0, it wouldn't really matter. The whole problem is we don't know if it's the teachers or if it's the intervention. So there's not really like a,
Yes, exactly. So what you want to do is shift your distribution to, one side of the curve where that teacher is that. Even if it's 70-30, it can be blown out.
oh, that's, yeah, what you want is an intervention that's effects are so huge that even if you got, yeah. The tricky thing is, and this is like on a later slide, I think, is that at least in the education world, and maybe this is different in the clinical trial world, our treatment effects are kind of small. Whereas the teacher effects, at least, first of all, there's a few caveats. One is that assumption of 10% is like a really big deal in this analysis, and it probably is totally wrong. It's pretty good, I think, in K-12, which is where it comes from, where people have done really good, like I think pretty decent studies of how much teacher effects vary. But there's very little similar work in higher ed, so like I have no idea if that's a good number. But the real problem is teachers matter a lot, and interventions matter kind of not as much. So you're just always going to have this problem, I think. But
So I get what you're saying about being biased rather than precision. The way that you're showing sensitivity, though, when you're saying where it would have significant amount. So if this were a million people, that would move south and it would like something much less sensitive. It's kind of leading bias.
yeah, so that's a good point. You're right. This threshold is totally dependent on the sample size. That's a good point. It would lower. This threshold would lower if you had a very big sample. But I actually think, you'd feel better then, I guess. Would you feel better? Yeah, I guess then you'd have to have a more extreme. You'd have to have a more extreme favoring of the program group teachers. Like they'd have to be even better, much more better. Yeah, so you're right. That's a good point. Maybe that's what your point was anyway, and I kind of misunderstood. But you're right. That's totally right. That's really interesting.
Maybe
Oh.
the target of the intervention should not be how, what the intervention is, but what the teacher.
Yeah. So that's totally true. So I actually originally used to do work in K-12 education, and there, like almost most interventions that people are studying are about kind of changing pedagogy or the curriculum or like the things the teacher are doing. And then I was very surprised that in higher education that is like not the case at all. There are now a few randomized trials that are more about like changing pedagogy. This is a little bit like a whole other topic, but in K-12, like a lot of the interventions are targeting teachers, and I think in part because of those estimates of how much teacher effects vary, it kind of drew attention to that as a potential solution too. It's like maybe we should have Teach for America where we recruit whole different types of teachers into the profession, or like maybe teacher professional development is like a really big deal, or maybe we should be comfortable firing teachers that are kind of at the bottom of the distribution, because if you could just hire people that are more average, that'd make a really huge difference. But yeah, I do think that stat in general, and if someone could mimic that in higher ed, might change the way people think about how we intervene. I do know that like in the K-12 world, where usually people are trying to change people's student achievement levels, that if you know people's prior achievement, it is like a very highly correlated with their future achievement. So if you have 6th grade math scores and you're trying to intervene to improve 7th grade math scores, like I think the correlations are like 0.7 or something really high, that how much of the outcome is kind of almost seemingly like predetermined. Other comments or questions? Okay. So the implication, which is probably obvious from the beginning, is that it's really hard to separate out the effects of the core components of a program that you might really care about and the types of teachers or surgeons or whoever else, service deliverers, that ended up in your program group when you use this kind of design. It's a bit of a concern. Some solutions you could randomly assign at the classroom level, either by randomly assigning whole classrooms. That kind of wasn't really possible here, but you could have randomly assigned teachers theoretically to this, and that would have kind of solved this problem. That's one solution. The con is it just seems like in higher ed it's been mostly practically infeasible to do this. In K-12, I think one reason that they've been more successful is because districts have a lot more control, and they often do randomize whole schools. So they get a district that's interested in some sort of reform, and the researchers and whoever's like reform it is bring a whole bunch of money to the district, so they're kind of interested, and then they convince them, well, sorry, there's not enough money for everyone, so we'll just give half of your schools in. And they do this in many districts, so they end up with 60 or 80 schools, and then they randomize at the school level. This hasn't happened yet in the higher education world. And whenever I suggest it at times, it never goes anywhere. So we'll see if someday it happens. But another option is to just only evaluate student-level interventions. So we've done evaluations of programs like performance-based scholarships where like there is not really a service deliverer. You kind of just tell people, if you do really well in class, we're going to give you $1,000. If you have a certain GPA and earn a certain number of credits. But that's kind of, so that works. You don't have the same bias problem, but it kind of limits the kind of interventions you can test. So that doesn't feel great to me. You can do these sensitivity analyses, but as we just discussed, like the problem is you're kind of always going to conclude, or you're very frequently going to conclude, I don't know what to make of the results now because the teacher effects probably swamp the treatment effect. So, and you could do non-experimental analyses. Like if you did this in maybe in K-12, or sometimes they have value-added measures of teacher effectiveness. You could then try to control for the fact that you might have better or worse teachers in those classes. But it's a little weird because you've done an experiment probably because you don't believe that non-experiments can do a good job for causal inference. But now to account for the fact that at kind of level 2, your teacher level, you might have some bias. Now you're going to trust the non-experimental methodology to correct the bias. So there's something inconsistent about that. So I don't know. This is my way of saying it's a problem. And I have some potential solutions, but they're not. None of them are fully satisfying.
Maybe what you've done is okay. I mean, it depends. If everybody's going to get what's better, then it's different. But if people are allowed to choose, you're essentially emulating real world. You're getting the best that these teachers can do because they don't want to do the group level or the group. And so you might have chosen the best design.
So I've gotten that before, and usually it comes in the form of lots of interventions bundle component, at least in my world. I don't know if they do as much in clinical trials, but definitely in education, almost every program we study has more than one component, and you usually can't disentangle them. So you might say, oh, this is just another component. Part of this intervention is learning communities, and part of it is the kind of teachers that teach learning communities. I think there's a difference, and I'm probably going to mess up explaining it, but I'll try, which, let me say why I think it worries me. Let's just say that there were these 20 teachers that taught in the learning communities and these 20 that taught in the control. And the students that ended up going to these teachers, they ended up doing much better, and these did much worse. But if it had nothing to do with the learning communities, it is true that these students that got the good teachers did better than they would have had they got the bad teachers, but they didn't do better, everyone, the group of program and control, they didn't end up any better off on average than they would have. And all you really do is like rearrange the deck, the chairs in the deck. You know, like you haven't helped anyone. I'm sorry, you've helped the program group people, you've harmed the control group people because they got the worst teachers kind of, but you haven't, the system hasn't gotten any better. Whereas I think when you bundle an intervention, you know, so in some of these performance-based scholarship interventions that we tested, some of them had an offer of a financial incentive as well as some advising. And in the end, we didn't know what made the difference. Was it the money or the advising? But I know what to do if I want to replicate those results. I should offer money and advising. Now, I wish I could know which one mattered more because then I could have a less expensive intervention if it turns out that if the money alone would have done just as well. But I can just bundle it. In the case of learning communities, what you'd have to do to kind of do the same thing, you'd have to like retool your school so that you only hire the kind of teachers that like teaching learning communities and do learning communities in order to kind of replicate those results, or fire the kind of teachers that don't. And like no one's seriously considering that. So I feel like that's how you would do it. But first of all, we don't really understand the selection process, so we can't do it even if we wanted to. And second of all, no one's actually going to politically really consider that. So it's a little, I think it doesn't quite work, but are you convinced? But let's say you did this study, and the only reason the surgery that worked was because the surgeons that were doing that surgery were the best surgeons. But really the other surgery was better, but they had the worst surgeons, so they ended up looking worse. What might happen is the field says, let's go with the great surgery that was actually just great surgeons, and now everyone's doing the worst surgery. Does that make sense? Like that's the kind of thing that could happen. But. Yeah, darn it. That's one other solution I meant to include. Sometimes that is an option, and that I think is kind of a cool solution. Yeah, to have them do both, so then you feel like there probably is balance. Yeah, I agree. That's a good one. Yeah, like I feel like contamination is like I think the word that we would use sometimes. That like there's two things that can happen. One is that you kind of just have an allegiance, so you just do a better job in the kind of thing you prefer. The other is like, can you really, especially like in teaching or in psychotherapy, can you really do totally different practices in two sets of classes? Now maybe if it's just about so this intervention had people co-enrolling in classes, and that was a big part of it. And that really the teacher doesn't do anything about. Like that's just them signing up for these classes together, so that you have like a community of students that all take multiple classes. Like that, you probably don't worry about this. But if the kind of pedagogy that was supposed to come out of this, because the teachers were supposed to collaborate, if they change their practices because of that experience, it's hard to imagine like, okay, in class A, I'm going to teach like this, but then in class B, I'm going to forget all that stuff that I thought was better and no longer do it. So yeah, there's times when I think that's a great solution, and there's times probably where it doesn't quite work. But all right, how are we doing? Oh, good. Yeah, so random assignment alone doesn't ensure that we have an unbiased estimator of the estimand that we want, and by estimand I mean like what was the thing that caused the effect. So I think it's really important for us to pay attention in our studies to what really is the cause. Probably like in certain clinical trials where like you're just doing drug versus placebo, it's not so bad, but definitely like in my world, everything, like understanding or trying to think about what the cause is just super important, because yeah, our interventions are flimsy sometimes and hard to get a handle of, and it's even harder to understand what's happening in the control condition. But,
Another question that I is now blue, but you talked about the students picking the learning program from the beginning.
Yeah.
They got randomized to that. So that would be like for us, they randomize people to treatment, they get to pick the treatment.
well, the treatment is like learning communities at large. I think here's what it'd be like. I think you randomize people to get surgery A versus surgery B, but then afterwards you get to choose which doctor you end up having perform it. Like there are 20 doctors like the way it really worked is there's 20 doctors that perform surgery A and 20 that perform surgery B. You get randomized to one surgery, and then you can choose which doctor, because maybe like there's one that's closer to your home, or I don't know, like.
Okay, so then I'm just asking, do you try to account for that or can that influence the discretion? your experiment, that's in one group and not the other. Well, but they're getting heterogeneity too, so maybe it doesn't matter.
Yeah, the control group is kind of scattered about, taking lots of different classes with lots of different teachers. Yeah, I mean, had they not self-selected which learning community they were in, but instead been randomly assigned to the learning community that they were in, which again would never have happened because they chose based on like course scheduling and things like this. But had that happened, then you'd have like random assignment to learning communities too, and you could kind of get a sense maybe of the distribution of the variation in learning communities' effectiveness relative to each other by just looking at your treatment arm only. On the control side, you actually could get, like that is kind of the way that they got that 10% number, that there was a couple studies where students were randomly assigned to teachers with no intervention, essentially, and then they were able to sort of say, well, now any differences in outcomes you kind of think of as being either because of estimation error or because of true variation in teacher effectiveness, and that's how they got that. So you could, if you had not self-selecting, but randomly assigning people to your post-random assignment groups, then you could gain additional information.
Yeah, well, it seems like it would be another objective, but I just wondered if it in any way influences sort of the main effect of this
Yeah.
Just curious.
I don't know.
Yeah, I wouldn't be randomizing the students in the learning groups, because what if they chose basically like, oh, all my friends are in this,
Yeah, totally.
and then this, and what if they're a bunch of really smart people, or a bunch of really people who don't want to do school?
Yeah, now, I mean, they're all, those people, once you've randomized into treatment or control arms, in the treatment arm, they did get to self-select which learning community they ended up in. But they're kind of all learning communities, so if your effective is kind of the average effectiveness of learning communities, I don't know. But yeah, you're totally right. Well, this is like a great segue to the next topic, but let me keep answering questions first. And then.
Was there any kind, looking at the whole pool of students, was there any kind of selection for
Oh, the study? Oh, that's a whole other, yeah, that's like, at least to me, that's a generalizability issue. And yes, yeah. These students, I mean, there's 1,500, so there's a large number, but they definitely were people who chose to be part of a study, who kind of were interested in learning communities. And there's a whole other set of students that never even signed up for the study because they were like, learning communities aren't for me. Why am I going to go enter a lottery to join learning communities? I don't want to join them in the first place. So there's definitely an external validity issue in most higher ed studies. There are a few of them where they've just randomized like the entire incoming freshman class kind of behind the scenes. This, at the time especially, because it was like the first one of these, you had to get informed consent from every single participant. Not that I mean, the risks are like pretty low. It's not medicine. Like the risks are a lot different, I think, so that sometimes you can convince IRBs that you can use passive consent. But yeah, any active consent, who knows what would have happened to the people who didn't want to do learning communities in the first place. Maybe they knew, I don't want to do group, like, be in this group or community. I kind of want to just go to college, do my classes and leave. And like, I'd actually be harmed by having to like deal with the same 25 people, 3 classes together. Oh, so now you want to find more. I thought this was enough of a problem. You're adding additional problems to what we're doing. Other questions, or should I try to move on to topic 2? Which is totally related, and it's actually builds on what we were just some of the things we were just talking about. All right. So second topic is about, it's like more in the statistical weeds a little bit, but it's about estimating the standard error of the impact estimator in that exact kind of study. And the same motivating example should work perfectly here too. And the idea here that I feel like probably is familiar to most of you is that there's this concern that outcomes of individuals in the same group, and here's where like the group arm distinction is like becomes even more important. So groups, I mean these post-random assignment groups that are formed within the treatment arm and potentially within the control arm as well, that they might be correlated, right? And so then the research has generally said you got to do something about this, and there's 2 main approaches. You can use kind of random effects models, or you can use fixed effects models. Or else your standard error will kind of be incorrect. Right? Is this familiar to people? Okay. So I think our main contribution to this was that it actually turns out that the source of that correlation matters. And that I think people don't think about what the source of the correlation is, and that some sources you really do need to account for, and others you don't. But because you can't actually, this is going to be like a depressing day, by the way, because I feel like it's all like negative news. But because you can't tell what the source is, I have some papers that are positive, I should say. These just happen to be ones that are like kind of a little hopeless. But because the sources are difficult to disentangle or impossible to disentangle, you kind of have to worry that you're getting your standard error incorrect. Yeah, gosh, I should have at least done one of the more positive papers that I've written. It's my mentor at MDRC is this guy Howard Bloom, who in the education world is like considered like an amazing experimentalist. And he, I feel like, is famous for like coming up with really elegant solutions to lots of problems that people were worried about. And then like I asked him if he wanted to work with me on the first paper, and I feel like he very much was like, I'm not want to be part of the problem. Like you're just creating more problems for people. So sorry that these talks are mostly about things that are like challenges that I think are important to be aware of, but that don't have like fantastic solutions. But here's another one. Okay, so here I just want to like try to go through what I think of as the three sources of these correlations in outcomes or variation between groups, you might say, when you after random assignment. And there's going to be three of them. The first is going to be provider effects that are going to cause people kind of within groups to look more like each other than across groups. Then the second is going to be peer effects, which I'm going to try to convince you guys to just ignore because I don't want to deal with it. And then the third is going to be that sorting process that lands people into the groups that they're in, which we kind of discussed a tiny bit before, and I'll try to make clear in a second. So again, we've got our random assignment of individuals to program or control. You get groups that are about similar. Then we have level 2, and this is a source of uncertainty in our impact estimate, right? So we're talking about standard errors, and the reason people know why we care, but the standard error we care about because it's going to determine the statistical significance and so forth. So one source of uncertainty in our impact estimator is going to be the fact that we did this randomization, but we could have ended up with a different randomization. We don't get an exact estimate of, or we don't get an exact truth. We just get an estimate of the treatment effect. So that's like one source of uncertainty. Another source of uncertainty, especially if you're in the kind of the random effects world, does that mean something different? Like you imagine that your providers, your surgeons, your teachers, whoever, are kind of like a sample from a population. So then another source is the providers that kind of ended up in your study. Like they're kind of thought of as like randomly sampled from a population, and you could have ended up with different providers that were better or worse. So that's like kind of another source of uncertainty. And so if we think of like these 5 as a group, these 5 as a group, these 5 as a group, you've got your providers. Oh, so let me just say one thing first too. Right now, the colors of these balls are supposed to represent like the outcome levels that people are kind of almost destined towards going to if they end up with like average providers. But then they get their actual providers, and you're going to see like what provider you get changes your color. So like this guy's got a blue outside and now he's green because he got like a good provider. So even though he was kind of destined at first to be like a bad outcome, he ends up getting a good outcome because he got the good teacher, I guess, or good surgeon. And so as a result of these good or bad instructors, the outcomes are going to end up being potentially correlated within these different groups. Or stated differently, there's going to be variability in outcomes across groups. And this is what like a random effects model picks up on. It kind of looks and says, here's how much variability there is within groups based on how much variability I've seen within groups, or let me say this better. There's a total amount of variability in the outcomes. And then it sort of says, how much am I observing within groups? And based on that, I know how much I expect to see by chance alone between groups. And anything that is observed in excess of that, I'm going to sort of attribute to the groups, like some sort of group effect. And that kind of inflates your standard error. Is that familiar to people, or does that make sense? Yeah. So the point of this was there's 2 sources of uncertainty in our impact estimate. One is this randomization of the individuals, and then 2 is kind of the particular providers which influenced people's outcomes. So now, as a second example, I'm just going to do this with peer effects, and here I'm going to like, just to simplify things, pretend like there are no provider effects. Like all providers are equally effective, all surgeons are equally effective. So there are these groups, but the teachers or surgeons don't affect your outcomes in any way. But what does affect them is your kind of peers, like they're sort of influencing you within your classroom in my world. This might, I don't know if this is as relevant in medicine, but definitely like in psychotherapy this could happen. You know, like there's one bad patient in your psychotherapy group session and they kind of just mess everything up and everyone does terribly. Anyway, so that worked, all right, good. So same kind of thing. Your peers kind of influence you, then you end up with this group that are like all bad, low outcome people, and this group ends up with all low outcome. These end up with all good outcomes, and you kind of have the same sort of issue. And that, when you kind of run a random effects model, will make your standard errors larger. And it kind of should, I think, because these influences actually change people's outcomes. But number 3 is going to be the third, the problem child, and that's the client sorting. So here, we had our randomization. Again, we're going to pretend like teachers don't really matter or surgeons don't matter, just to simplify things for a minute. But what happens is that after people were randomized, they end up sorting into their groups. And maybe they just happen to sort in ways that are related to their outcomes. And then, like in my learning communities example, and maybe this, you guys can think of the analogy for you, this could be that a group of friends ended up getting assigned to the learning communities group, and they were the really smart kids, so they kind of all signed up together for one class. And then the kind of like not so smart kids, they signed up for another class. Or it could be like a time of day thing where like in community college, they oftentimes offer classes like during the day and at night, and it could be that the nighttime classes are mostly attended by people who work. That's why they go to the nighttime classes, and maybe people who work, that's kind of correlated with having less good outcomes. So maybe the nighttime classes have the low-achieving students in the daytime. So anyway, you can imagine how this all might happen. But the important thing here is that when you end up with your outcomes correlated because of this sorting, you haven't actually changed people's outcomes. The only source of uncertainty here really was that first randomization. I'm kind of assuming people just moved where they were, but their outcome kind of remained the same. So there's no new uncertainty. But when you run a random effects model on data like this, it doesn't know what caused there to be these correlations. It doesn't know why these 5 outcomes look similar and those look similar and kind of these groups are all green. It just says there's too much variability between groups. I got to do something about that. I'm going to inflate the standard errors. And it shouldn't inflate them, and so you're screwed. And so the challenge here is that all 3 of the things I just talked about, they're going to contribute to why you might see excess variability between groups and outcomes and inflate your standard errors, but definitely the first one you should be wanting to do something about. The third one you want to be doing nothing about, but you don't know which one it is, because all you get in the end is data that looks like this. Does that make sense? Yeah. So it depends if you use random effects versus fixed effects. When you're doing fixed effects, you kind of end up sometimes, especially if you use like fixed provider effects, you end up oftentimes decreasing your standard error because you think you've kind of used these fixed effects to sop up some of the variation in outcomes. So I think in fixed effects, you'll usually end up with standard errors that are smaller than you wish. In random effects, I think 9 times out of, I think mostly you'll end up with inflation of standard errors. But I can imagine like hypothetical unlikely scenarios where that is maybe not the case. How to describe how that would happen. It could be that like students sort, or whoever, your individuals sort in this sort of a way, but then because of how that's related to how effective the instructors were, the surgeons were, that in the end there's no actual variation in outcomes between groups because the sorting led to really high potential achievers in this group, but then they got the really crappy instructor, so it kind of brought them down. And like if some weird correlation like that happens, I think you could have the opposite. But I think in general, what you're going to have is standard errors that are slightly too large. All right. This is the part where you're supposed to glaze over a little bit, I think. But that's the main point. I feel like if that all made sense, then probably like it's better to read the paper to understand the details, because I'm going to now do a really crappy job of trying to explain a little more of the math behind it. All right. So the guys I partnered with on this paper are like real statisticians. I'm like not a real statistician. I think I figured this out, so I feel like I deserve some props for that. But they formalized it and like made it really mathy. I convinced myself that it was correct by doing a simulation because that just is easier for me. If you want to read the paper, let me know and I'll send you it and you can read the more mathy stuff. But I just was like, let me just simulate data that kind of approximates these situations to convince myself that my intuition was right. So I'm just going to walk through the simulations that I did. Unless you want to just ask more questions before I do that. But yeah? All right, I'll walk through. So basically, I made the simulation where individuals were always randomly assigned to an experimental arm, 50-50 probability. T is like, are you assigned to treatment or control? I made it so that there was no treatment effect ever. Never any treatment effects. I did this so that providers were randomly selected from a population, the way sort of a random effects model is supposed to be kind of having you think, or if you're kind of estimand is supposed to be thinking of your providers as like a sample from a population. I made this hypothetical study huge so that I kind of would have very precise answers to the things I was going to ask. So there's 10,000 patients, and they were all in groups of size 25. I did 25 because that's like a common classroom size in education, but you could probably redo this for whatever a common number of patients that a doctor might have. but it probably shouldn't matter a huge amount. And then what I did was I varied two different factors. One is how were individuals assigned to groups within their experimental arm. In one case, I had them so they're randomly assigned, which I think you're kind of assuming when you run if you want to get the standard errors correct, basically, you kind of have to assume that. And the other times, I had it so they were not randomly assigned, but instead they were assigned to groups in some way related to their kind of outcomes. So that kind of like the high achievers were in group 1 and the low achievers in group 2 and so forth. And then I also varied whether or not provider effects kind of vary. So in some cases I have it so that all providers are equally effective, and then in some cases I have it so there are kind of good providers and bad providers. And I do that because the reason that a random effects model is kind of supposed to get you a correct standard error is, or when it's going to, is when provider effects actually matter, where there's variation that you need to account for, and then it's going to kind of inflate your standard errors. So I wanted to have a case that kind of favors that. So I think there'll be 4 cases that involve these 2 options and these 2 options kind of crossed. All right, so I estimate the effects using 2 different models. Like one is like kind of the naive, what I think people would normally think of as a naive model, but is not recommended in the literature, which is to just use kind of OLS, just a regular simple model where you've got, I think I actually did this, yeah, Y is your outcome, T is your treatment indicator, E is some error term that's assumed to be normal with a mean 0 and a standard deviation. I think I made the standard deviation 1 in all these examples. And then your standard error estimator looks like this. So it's kind of a function of how much variability there is in the outcome, plus T times 1 minus T is always just going to be 0.25 because I've made T bar, that's the proportion assigned to treatment, 0.5. And then N is this 10,000, so you'll see that come up in a minute too. But that will be the standard error estimator. And then I also run the random effects model, which is I feel like what a lot of people in the literature would say to do, same kind of thing. But now we've just added this new term, which is the kind of random effect for the group J, to which the individual ended up sorting, mean 0 and standard deviation of what I call tau. All right. These are the 2 models that I'll kind of have competing against each other. And this is the standard error form. It's a little more complicated for a random effects model. But this front part actually is identical to the last slide, this part right here. It's just the total amount of variance over N times T times 1 minus T, which we saw. But then there's this new thing, and that's the thing that inflates your standard error when it turns out that there's variability between groups. So when it seems like there's excess variability between groups, then you're going to have a positive value of tau here, and you're going to end up inflating your standard error. I don't know if that formula is familiar. It doesn't really matter. If it is, like, yeah, the math of this doesn't matter that much. It's like the ideas, I think. But so first data generating mechanism that I made is you have people randomly assigned to treatment or control, and then once you're in the treatment group, you get randomly assigned to or once you're in the treatment arm, you get randomly assigned to a group that will have a certain provider, a certain doctor. And now there's no provider effect. So then what provider you get, it doesn't really matter, actually. They don't increase your outcomes or decrease them. You're just wherever you were going to be. So this is kind of what a data generating mechanism like this looks like. Your outcome is just a function of if you're in the control group, if you're in the treatment group, I set the treatment effect to 0, so this is 0, so like it doesn't matter really. And then all that really matters is just where you happen to fall in this, like at this individual level error distribution. So in that case, under this kind of a scenario, the true standard error should be somewhere around 0.02. The 0.02 is just because I did like 10,000 simulations and it's not exactly true, but it's 0.02. Whether or not you use OLS or the random effects model, you end up on average across lots of simulations getting a standard error estimate that's correct, which I think this we kind of expect because we've got the good stuff going on. There's random assignment of people to groups after they're randomly assigned to their arms, and providers don't matter. So there's no need really to have used the random effects model. You could use either one, but you get the kind of correct standard error. So there's no bias. Your percent bias is nearly 0. Your probability of rejecting the null, given that there's no in the simulation, there's no treatment effect, so it's right. This is just showing you the formulas as to how like that everything's kind of working the way it should be. That's the formula for the standard error I showed before for the OLS model. That's the standard for the random effects model. And the key thing here is that term on the end, which is the interclass correlation, or tau squared over sigma squared plus tau squared, it's now 0 because you randomly assigned people to groups after randomly assigning them to the treatment arm. Nothing happened to those groups that was special, and so there's no excess variability in outcomes between groups, so you have a tau that's basically 0, and so everything kind of works out. So if, in this world, it doesn't matter what model you choose, you're kind of fine. Here's like the first horrible problematic case. Here, there's now non-random sorting into groups. So this is the case where like your best students ended up all jumping into this one group, your worst students end up in this group, and that's going to cause problems. There's no provider effects, though. So the actual data generating mechanism is exactly the same as I showed on the last slide. The only thing that happened was that after people's kind of outcomes were generated using a model that looks like this, they grouped in this sort of funny way that led outcomes to appear correlated within groups, or that there's kind of this excess variability between groups. And what happens now is the true standard error should be exactly what you saw last time. But what happens is if you run OLS, you get things right, which is kind of reassuring. But if you run the random effects model, it now thinks, oh man, there's like provider effects or something, that there's this big variability in outcomes between groups, and it inflates your standard error, and it's just really wrong, like really wrong. Like really, really wrong. Does this make any sense? Yeah? Yeah. I think it is wrong. I mean, to me, and by that I mean, like, we know the truth. Like, we know how much uncertainty there should be in our impact estimate, and it is incorrectly claimed. Like, it thinks that there's much more uncertainty than there is. If you re-randomize your people over and over and over again, and kind of look at what your treatment effect estimate is for 10,000 times, which is what we've done, and then you look at the standard deviation of that, what you get is 0.02. That is the truth. That is the correct standard error. But what you actually get, what your model will estimate is, I just think, incorrect. It thinks there's a lot more uncertainty than there really is. I think that's sort of how these simulations.
Yeah, I think that's because how you tell your data or your program to perform, right? Because you're still in the second level, not a random process. Getting a bigger standard error.
Well, I don't think you. When you tell your program, do you mean you don't run a random effects model?
No, it's because you use the random effects.
Oh, yeah.
It's coming from the correlation of that.
Yes. The problem, well, yeah. That is correct. But the problem is going to be that when you get your actual data, you're not going to know why it was that there was correlations in outcomes between groups, or why there's excess variability. You don't know if it's this random sorting, or if that there really were provider effects. And you'll see, like on the next slides, when there really are provider effects, then OLS gets it wrong. It's way too small, and the random effects model gets it right. But the problem is, you don't know what scenario you're in the real world. Like, you don't know, was it that I had these really effective teachers that made all these outcomes look really good in this group? Or was it the kids sorted and all the really, you know what I'm saying?
I guess what you're saying is that you're not asking the same question if you have a non-random sorting groups, and so that's why.
And in reality, when you have your data, you never know what's going on, right?
Well, that's the point.
The random effect model will, in general, account for your uncertainty a little bit better than your fixed effect model.
Well, I guess what I'm arguing is no. Like, if it turned out that you had this sorting that led to these different outcomes, your random effect model is going to tell you this. It's going to say you're very uncertain about your impact estimate, but you're not actually. You shouldn't be. It's wrong. It thinks you're more uncertain than you really need to be. I don't think so. Yeah. But keep pushing me, because I feel like.
You're saying the true estimate of your standard error of the
True.
provider effect is 0.02, but that's not what the question you're doing when you do a random effects model. You're trying to see what the estimated standard error of the provider effect and whatever non-random sorting is.
So I'm talking about the standard error of the impact estimator, so like beta 1. And if you thought of this as, this is the data generating model, but you can, I guess when I go back, I'm talking about the standard error of this or the standard error of this. Well, one of the, either one of those, whichever model you end up running.
I guess what I'm saying is the assumption for a fixed effect model under most scenarios is unlikely to be true.
Oh, meaning that the assumption there is that providers are like all equally effective. Yeah, that's totally, I agree with that.
So my argument then is perhaps using random effect model is slightly better because there's not very uncertainty.
And I guess I'm saying, well, okay. When providers do matter, so let's go to the when providers do matter, that they do, like, so not the kind of fixed world, and then maybe that will get us to the point where we can continue this. Because I don't think you're going to be convinced even after, but at least we'll be closer to seeing that. We'll get closer to a scenario that I think you'll like. Okay, so let me just do two more, and then hopefully that will lead to like So the next case is what I think you want to be the case, which is your clients randomly assort to their groups, and there are provider effects. So there are some providers that are really effective, some that are less effective, and they vary along some sort of distribution. And I've made it so that this is sort of what the distribution is, that providers, I actually use that 10% assumption, that they're kind of accounting for about 10% of the variability in the outcomes. And when you have that, your true standard error should be 0.0388. Doesn't matter. It doesn't really matter what model you use. That just is the truth about how much uncertainty there is in your impact estimate. OLS will get it totally wrong. It's way too small. And your random effects model will get it totally right. Since we're out of time, I'm just going to go to the next one, which is, let's just say, though, that both these things happen, which probably is the case in the real world, that providers do matter, that they vary in their effectiveness, but there also might be non-random sorting into groups. Now, the truth remains here. That's just simulated data, so we know the truth. Now, OLS is too small, again, because it's not accounting for the fact that there's these correlations in outcomes. But random effects, again, it's too big now, kind of as you anticipated. It thinks there's much more variability between groups, some of which was caused by the providers, and that you kind of wanted to account for, some of which was caused by these sorting into these groups. You didn't want to account for that, so it's inflated the standard error, and it's too big. It's bigger than the truth, the known amount of uncertainty in your impact estimate. Is that? You're not.
If you don't know the sort of whether it's random or not, should we be willing to
Well, I think that's one argument. Yeah, like why not be, it's like, I think people would call that conservative. I would call it upward bias, like you have an upward bias standard error. Yes, but then you're going to have trials that don't find significant results even though you should have. And like in my world, where, and I'm sure this is true in your world too, where like every sample member you recruit costs a lot more money, I kind of don't want to have to overpower all my studies because of the fact that I'm getting my standard error wrong. So, but yeah, I think there's one way to go is to just use the random effects model and kind of know that you probably have a standard error that's bigger than it needs to be. Yeah, that's definitely an option. And I think if I had to like recommend something, that maybe that probably would be it. Like just. Yeah. Well, yeah. But the thing is, I wouldn't say it's proper. That's the tricky thing. You're saying properly sized, and I'd say like too big because you're going to think there's more uncertainty than there is. Yeah, you're right. That's fair enough. You're still not convinced that it's even incorrect. Like that it's even incorrect.
I think we're on the same page, but the way that I would interpret the data is, your standard error, your true standard error is probably between 0.02 to 0.49, right? So
That's another way to do it. Yeah.
yeah, so like these two discounted your boundaries for your standard error. So I'm not bothered by that. I mean, all you need to show is that if you're not thinking about statistical testing, that's in the estimation framework, you can always say the close estimate is probably close to your estimate.
Yeah. Fair enough. Yeah.
Yeah, I was just going to comment that this is probably the most likely scenario. The one that
I think so.
you probably wouldn't like to have income. The choice of going with the random effect there is just get better, just percent bias.
Oh, in terms of percent bias, yeah, that's true. If your like favorite measure is percent bias, I'd agree. Yeah. Yep. Yeah. I mean, I wish there was a way you could just kind of adjust it down or no. So, but because we have underpowered trials, right? Like we're almost always doing trials that are too small to begin with, and now you're making it even harder on yourself. So that's kind of like the disappointing thing, maybe. I should say, like we've ran through this, like the scenarios I just laid out. The data generating mechanisms kind of aligned with the way random effects people think. Like the instructors or surgeons or whoever were literally randomly sampled from a population. The fixed effects people, I don't know where your world like lives. We write up how you should think about this if you're that kind of person too. And in those scenarios, like we always simulate like that there's the exact same 50 providers in the treatment group and there's the exact same 50 in the control, and you use the kind of model that a fixed effects person would might recommend, at least that I've read that people recommend. And it's interesting that the results are kind of like the reverse there. Then your OLS gives you standard errors that are a little too big, and your fixed effects will give you ones that are kind of too small. In this case, where there's sorting, and providers do vary in their effectiveness. But you can read the paper if you're more of a fixed effects person. You can read about that also. But some practical guidance are that usually I think of including covariates in models as trying to improve the precision. But it also turns out that if they account for that post-random assignment sorting into groups, not treatment arms, but groups, then it actually can help you out here. Like it'll make it so that your standard errors are more close to correct. you could try to control your assignment to providers. So if you were like the experimenter in control and make sure that your individuals were randomly assigned to their groups, then you're also kind of good to go. Then the random effects model will work perfectly well, or the fixed effects model, depending on your kind of preferred inference. So similarly to the way if you're like a non-experimental researcher and you want to kind of account for selection bias into treatment arms, you can use like baseline questions to help model treatment arm selection. You can do the same thing here, where you try to ask baseline questions that will likely indicate what provider you'll end up with or what group you'll end up in, and that will help you out as well. Yeah, and then this is, I think this is almost what you all are recommending is if you just kind of know the issue, then you know probably the directions of the bias, you can do things like bounding, where you just kind of assume when you do random effects, you're probably getting a standard error that's a little too big, but OLS might be like very much so too small. So somewhere in between, hopefully, is correct. And if you're the tricky thing is you can do when you do your study and the results change depending on which you use, and then you're not quite sure how to explain it to people. So, all right, that's all, and I'm out of time, so.